Hi Erika, how are you? I saw your work and it wasn't so bad. Maybe I could pinpoint some few things. So when you are proving about the cardinality of that set, let me just go to this picture. One moment. So judging by what you wrote here, something I would like to mention is that you see, why is it not writing? Oh, okay. So you see here you wrote S equals x n running from 1 to n. And then you wrote 1, 2, 3, 4, all the way up to n minus 2, n minus 1, and n. Notice the set you're talking about is not arbitrary. It's not just any set, because these numbers are elements of the natural numbers. So somebody can think that you are talking about natural numbers, but I think the proof was to be about a whole set. So let me show you how I would go about this one. This is how I would do it. I want to prove that the cardinality of the power set will always be greater than the cardinality of the set. So let me write. So the cardinality of the power set PS is greater than, let me use ones, is greater than the cardinality of the set S. So that is what we want to prove. Okay. So we would have two cases. Actually, we would have three cases, but I think I'm just going to cover two. I will cover the first case where S could be empty, right? So we can have case 1 where S is empty. So case 1, assume that S is the empty set. Okay, so if you make that assumption, notice if that is the case, it follows that the cardinality of S is 0 because the set has nothing. Okay, but the cardinality of the power set of S is going to be 1. And do you know why it's going to be 1? It's because if I was to write the elements of this power set, notice that the power set of S, the power set is the set of all subsets of S. Notice S is an empty set, and an empty set is going to be a subset of itself. So we are going to collect one subset, which we are going to call the empty set. Okay, and what is the cardinality of PS? It's going to be 1 because it has one element inside it. Okay, now since 1 is greater than 0, then we conclude that the cardinality of S is less than the cardinality of the power set of S. So in that case, we have shown that even if S is empty, we would still have the cardinality of S being less than the cardinality of the power set of S. Okay, so let's move on to the next case. And in the next case we have, for the next case we are going to have a finite set S. So case 2, assume S is finite. Okay, so if S is finite, then what does it mean? So we're going to say that if S is finite, then S equals S1, S2, S3, all the way up to Sn. It has got n number of elements in this case, so we can say for some natural number n. Okay, yeah, I need to expand this board. How do I do it? So S is a finite. So if S is finite, then it's going to contain these elements for some natural number n, meaning it has n number of elements. So what do we do next? What will be the power set of S? So by definition, PS, the power set of S, is going to contain, of course it's going to contain the empty set. It's going to contain the singletons S1, S2, S3, all the way up to the singleton Sn, and it's going to contain sets with a cardinality of 2, that is something like S1, S2, and it's going to go all the way, and even the whole set S, it's going to be inside there. Okay, so what if we were to have a one-to-one function between S and the set PS? And let's define that one-to-one function and see how it's going to behave. So let's move on to the next page and see what we can do about that. Okay, still new to this. Alright, so next, what do we say? If we define a function f from S to the power set of S by fa equals a. So this is a function that is mapping every element of the set S to the singleton element in the power set. Okay, so if I was to take you back here, you're going to notice that the function is going to map S1 onto the singleton S1. It's going to map S2 onto the singleton S2. S3 goes to the singleton S3, and then Sn goes into the singleton Sn. Okay, so what can be said about this function? It follows clearly, we can say clearly f is injective, but not onto. F is injective and f is not onto. Injective means one-to-one, of course. Okay, also it is obvious that or we can say that it's not onto. We know it's not onto because the codomain of F properly contains the range of F. So let's pause and think about that statement. You see, the range of F is going to be, this is the range of F, okay, where F is mapping the elements of S. So this is the range of F, but the whole power set is the codomain of F, okay? So we don't have a bijective between S and the power set of S. And so, having said that, okay, again, that shows the presence of other elements inside the power set of S, and those elements are not part of S, okay? So what do we conclude? We say, conclusion, since it is impossible to have a bijective map between S and PS, okay, so what do we say? Then we conclude that the cardinality of S is less than the cardinality of the power set of S, okay? Yeah, so that's how I would prove it for the finite case, okay? That's my proof for the finite case. Started here, and then there was the proof for the empty set, which started there, okay? So the other case is going to be the infinite case. So what if S, what if S is an infinite set? Or what if the cardinality of S is infinite? What would happen? Okay, so that is something nice to think about, because infinity has not yet been defined, and I don't know whether it will ever be defined. Okay, all right, so well, that's it. I hope to see you soon. You can think of booking a lesson and we can discuss some of these things. Yeah, and have a nice time. Bye.